concerned on your future courses that you apply what I teach you. Okay, that is, I think, more important to me than anything else. Right. So from here, I know some of you say that is completely bullshit. I want to know, have a good grade. It's up to you, okay? Right. So from here, we want to find. Okay, so next we want to find the second moment of area. Okay, we're going to find the second moment. So second moment of area for this case is equal to IZZ is equal to width depth cube divided by 12 plus by area multiplied by global centroid minus by individual centroid, and this whole thing will be squared. Okay, so watch this. Okay, watch this. I'm not even looking at the figure now. I repeat again, I'm not even, now the figure is halfway. I'm not even looking at the figure. So I'm going to do this, okay? IZZ1. So this is equal to width is equal to 160. Depth is equal to 20. Cube divided by 12. Cross-sectional area is equal to 3200. Multiplied by big Y bar is equal to 35. Minus by small Y bar is equal to 10. The whole thing squared. So this will be equal to 160 times 20 power of 3 divided by 12 plus by 3200 times by 35 minus by 10 squared. So the whole thing is equal to 210. So I think I better break it down. So it's equal to 160 times 20 power of 3 divided by 12. So it's equal to 320 times 10 to the power 3, right, over 3. Then plus by 35 minus 10 squared times by 3200. So this is equal to 2 times 10 to the power 6. So this whole thing will be equal to 210, 2.1067 times 10 to the power 6 millimeter to the power 4, or is equal to 2.1067 times 10 to the power minus 6 meters to the power 4. So we found one of our second moment of area. So the second IZZ2 is equal to IZZ3. I like to highlight that I cannot see the figure now, but I know that this is equal to 20 multiplied by 80 power 3 divided by 12 plus by 1600 multiplied by 35 minus by 60 squared. Okay, so this will be equal to 80 power 3 times by 20 divided by 12. Okay, so this will be equal to 2560 times 10 to the power 3 over 3 plus by 35 minus 60 squared times by 1600 is equal to 1 times 10 to the power 6. So this will be equal to 2560 power 3 divided by 3 plus by 1 power 6. So it's equal to 1.853 times 10 to the power 6 millimeters 4. So this is equal to 1.8533 times 10 to the power minus 6 meters 4. Okay. So I did not do anything magical. Okay. It's just how we arrange the data to calculate the second moment of area. Okay. So what do I mean by that? Can you all see the trend? I did not look at the figure, but I know this will come to here. This will come to here. This will come to here. And then this will come to here. And then this will come to here. I just look at the table. Because of how I've designed the table, you can directly plug in. Why do I do that? Because in your final exam or your term test, I'm going to give everyone different magnitude for the what? Second moment of area. Okay, and this is how I'm going to do my programming. Right, so the next one, if you look at the section number 2 or 3, right, you look at this over here. So this is, hey, Eugene, wakey. So this will come down here. So right, 20 will come down here, right? 80 will come down here. I hope you can see the pattern, yes or no? Then 160 will come down to here, right? You don't need to look at the figure now. Once you got the table sorted out, you're good to go. 35 comes to here, and then 60 comes to here. Okay. So I've done a lot of Excel spreadsheet on customized second moment of area. You just change the numbers, and there you go. You get your value. Okay. I hope you adopt this because it will minimize you making mistake. A lot of students, when they don't follow this, they look at the solution manual. They just, okay, I'm going to follow the solution manual. You always will make mistake. Okay, so I hope you adopt this. So from here, finally, you can adopt what is IZZ. Okay, so IZZ is equal to IZZ1. Okay, IZZ1 plus by twice of IZZ2. Okay, why twice? Because IZZ2 is equal to IZZ3. So this is equal to 2.1067 plus by twice of IZZ2 or 3, 1.8533 times 10 to the power minus 6. So this will give you 2.1067 power minus 6 plus 2.18533 power minus 6. Hey, 533 power minus 6. So this is equal to, wait, 2.18533 power minus 6 plus by 2.1067 power minus 6. So I'm getting not the right answer. Minus 6 plus by 2.1067 power minus 6 is because, so it's equal to 5.1833 times 10 to the power of minus 6 meter 4. Okay, so we have just found our IZZ. So we have found our IZZ. Okay, so this one is now known. And then the next one, we're going to find our QZ. Okay, we're going to find our QZ. So what we're going to do for QZ, okay, I'm going to do something different. Okay, so where we are now, we have done centroid. We're going to done first moment of area. So now, as I said, I put an extra portion down here because I want to find the shearing stress distribution equation. For that, the first moment of area is also going to be a what? Equation. Okay. So we are going to develop an expression for first moment of area. Okay. And it's not that difficult at all. Okay, it's not that difficult. So what we are going to do now, okay, is we are going to apply what we have written on page 3. Okay, so we're going to apply. If you ask me, Eugene, what are we going to do now? We're going to apply this portion. Okay, we're going to apply this portion, right? And we're going to apply this portion. Okay, to find the distribution. So if we are going to apply those two equations, okay, we're going to apply those two equations. All right. So I need a lot of space. I'm going to start from a new page. Okay, I do need a lot of space. Okay, right. So I'm going to copy the diagram again. Hold on, I'm going to copy the diagram. I need the diagram to be big. Okay. So there's two new terms that I want to introduce to you all. Okay, there are two new terms that I want to consider, that I want to mention to you guys. So the top horizontal portion, okay, the top horizontal portion, this is what we usually call the flange. Okay, And these two over here is what we always usually call them as web. Okay, so this is our direction based on Vy. So that is our flange and that's our web. Okay, so now we knew this, that the horizontal, right? So this is our ZZ, right? So from our ZZ, we know the distance from here to here now is 35 millimeters. We know that. Okay. So the first thing we're going to do, so I'm going to copy the rules again. Okay, we're going to copy the rules. Okay, so this is our rule. Okay, I'm going to keep it small still, that y'all can see, right? So the analysis, so one of the analysis says what? The analysis will be carried out from Y variable maximum. So we are going to look at Y variable maximum, right? So we are going to first look at the flange section. Okay, so we're going to consider flange section and the limits. Okay, we have two limits. Okay, so the maximum is easy. The maximum is equal to 0.035 meters, right? The minimum, what is the minimum? So you take 0.035 minus by 0.02, right? Minus by 0. Why 0.02? Because this is 0.02. Okay, so we are going to have a limit from 0.015 x, sorry, not x, it's y. Okay, we are looking at y. I do apologize. To 0.035. Okay, so that is the limit that we're going to form. So basically, for this flange section, we are going to look at this region. Okay, but for this case, I'm going to teach you how to find the distribution equation. Okay, so now I'm going to draw. We're going to draw the flange section. Okay, so this is a flange section. And then this is the centroid. Okay, so this is our centroid, right? So now we want to stop. So our variable, we're going to stop somewhere around here. So this position is, I pick an arbitrary distance. Okay, so this is an arbitrary distance. So now this is our y, right? This is the area of interest. Okay, this is the area of interest. And at one point down here, exactly at one point down here, where the distance at the top and the distance at the bottom are equal, this is where we get our y bar. And the y bar will be from the what? Will be from the datum. So this is the pink is our centroid. And the pink is also now known as our what? Our datum to find our first moment of area. Okay, so we also know that the extreme point, this distance over here, is our what? Our y max, and this y max is equal to 0.035 meters. Okay, and this also corresponds to equal to what? C. Why I call it C? Because when you look at what we are trying to derive over here, right? We call this point what? We call this distance what? We call this distance what? C. You see that? Okay, so that's your maximum distance. So from here, we're going to calculate our QZ. Okay, so QZ. Why QZ? Because our first moment of area will be taken from the z-axis. Okay, the datum, the centroid, where the datum is, the first moment of area is about the z-axis. So first moment of area about z-axis, and we're going to focus on the flange. So this is equal to A right? A y bar. Okay, so we're going to take width multiplied by depth multiplied by y bar. Okay, so we know a single value down here, the distance from here to here